Welcome to the dynamic learning hub of ExcelR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. A hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. ExcelR. We don't just train, we build careers. Welcome to the dynamic learning hub of ExcelR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. A hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Want to get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. ExcelR. We don't just train, we build careers.
So good evening, everyone. I hope you can hear my voice. Yeah. Okay. I hope my voice is clear. It's fine. Okay. Good. Great. So let us start the session. Right. So good evening, everyone. This is day 10 of our session on Gen AI and Agentic AI. So let us continue. From what we have left off in the whole session. So let me share my screen. So great. So we'll start. Okay. So let us continue from an important topic, right? So what is LSTM? Okay. So it's a very, very important topic, I would say. Okay. Okay. So right from this topic of LSTMs only, the concept of transformers has come, right? And these LSTMs are very useful in building up for attention mechanism and then for the concept of transformers and so on. So we will see each of the topics in theoretical as well as the practical part as well. Okay. So first let us see what is an LSTM. Okay. So first of all, what is LSTM? So LSTM is a long short-term memory. So that is the full form of what is an LSTM. So what exactly is this LSTM? It is a type of RNN architecture. So what is an RNN architecture? RNN is nothing but recurrent neural networks. So we have already seen what is an RNN in the previous session as well. So basically RNNs are nothing but a deep learning model which is basically used for sequential data or a data which occurs with actually a time, or right, you can say, yeah, sequential data or a time series data, right? Or textual data we can see, because text data occurs in a sequential order. So whatever happens in a sequential order, right? All those things actually come under RNNs, or that particular architecture is called as an RNN architecture. Now, if we try to understand what is this LSTMs are there for, right? What are these actually doing inside I would say, deep learning, and why these are, or what these are especially doing inside the generative AI part, what we are actually trying to understand, right? So, talking about particularly LSTM and saying about that, this is an RNN architecture. There are a few problems when it comes to RNN. So that particular problems are mostly, I would say, I will not say that all these problems are addressed by LS teams, because if everything is whatever issues are there in RNN, if everything has been addressed in LSTMs, we would not have attention mechanisms, and after that we would not have this transformer mechanism. So these two would not have been there, right? So trying to understand that what are the problems in RNNs and what are the issues in what are there in RNNs which have been addressed by LSTMs. So till what extent this LSTM has actually overcome this problem, right? So that is very important to understand. Now, talking about the RNNs, first of all, why LSTMs have come, right? The main issue in RNN, so this also, I just gave a bit of intro coming, what happens in this RNN. So RNN is actually facing with an issue called as a vanishing gradient problem, right? So what is this vanishing gradient problem? We will see. And these LSTMs are basically found, or I would say they are, came into existence in the year 1997. So these are far ahead, compared to this attention mechanism, or when it comes to transformer technology. It is a very earlier mechanism. What has actually these LSTMs are there for. So this is the image where you can understand. This is bit of having a bit of math. Okay, so in a simple term, try to understand. So what is this vanishing gradient? As I told, so vanishing gradient is nothing but applying derivatives. Okay, so for example, if we use an activation function, and I just told you a glimpse of what is an activation function. So activation function is basically nothing but a function, or I would say it's a statistical function, which actually implies, or or I would say it would help in a simple language. So it helps from building of one layer to the other layer, right? So what are these layers? These layers are inside the deep learning model, I would say, or the model with more layers, right? So this we have discussed in a briefer notation. So these activation functions helps in I would say building a neural network, or a network model, where on that we can train the data and predict the outcomes. So in that process, what exactly is happening is, when we actually calculate the derivative parts, right? So that derivative is actually tending towards zero. So that is that is a huge issue when it comes to so if you see the formula, right, you can see that dou L by dou W. So it's actually called as a partial derivative. Okay, so usually one such example is the using of sigmoid function. Okay, so sigmoid function is nothing but nonlinear function, which is I would say it's called as an activation function. Okay, so I probably I know a few of you might be pretty new to this concept of activation function, gradient laws, chain rules, right? Sigmoid function, back propagation, forward propagation, right? So if you are aware of it, it might be in a better. I'm not touching those upon very deeply, because that becomes more of like a deep learning class rather than generative AI. So that is the reason I was not touching that much on that particular aspect. But you can try and understand that if the derivative becomes zero, right? So there is no particular function which is left over if you are applying a partial derivative. So that is the vanishing gradient problem. Okay, so to overcome this problem inside RNN, the concept of LSTM has actually been, I would say, has been actually researched and developed in a single line. Okay, so let us go to the next function, which is the bidirectional I would say next is the bidirectional LSTM. Okay. So bidirectional LSTM, or I would say bidirectional concept is only what BERT is actually being using kind of right now. So what is BERT? BERT we have seen. BERT is actually the transformer technology what Google has actually found, right? So whatever now we are doing, Google search, autocomplete, everything is basically BERT technology. So it is actually built on the function of bidirectional LSTMs only. Okay, so now talking about bidirectional LSTMs. So these are basically an advanced form of LSTM, right? And the main, or I would say the main pro, I would say, or the main advantage we can say of using this bidirectional LSTMs are applying the model, or understanding the data from both the directions, whether it is from the forward direction or whether it is from the backward direction. So what happens is, if you are giving a particular sentence or a sequence of words as a form of a sentence, the the data actually captures from both the directions. Okay, so it captures from both the directions. So it tries to understand the context, right? Not only from one direction, but it tries to understand from both the directions. So that is the advantage, particularly of using the bidirectional LSTMs. So that is, see, why we are using the bidirectional LSTM. So the input sequence. So as I told, the forward pass captures context from the beginning to end, and then the backward pass captures from the end to the beginning. So in both the directions, it will try to understand the context in the sentence. Yeah. So some of the use cases, what we are applying or what we are using these bidirectional LSTMs are named entity relationship recognition. So this we have actually have seen in practice. And then we have parts of speech tagging. So even this concept of practical we have seen. So text classification and machine translation is also a couple of concepts which are the use cases of bidirectional LSTMs. So that only we are using in the current scenario as well. So classifying the text or machine translation and so on. So this is the architecture of in a simple way how the forward and the backward LSTMs actually work. Okay, and I've kept it very simple for you to understand. If you want to learn about LSTMs, it becomes a bigger concept. Okay, and I don't want to spend so much of time on LSTMs as well. Might be if you might be aware of that. If you still need, because I'm covering mostly attention and transformers, which are and I'm focusing more on transformers as well, because transformers is what currently is running as a technology inside the generative AI. So I feel because this is a bit outdated actually, I would say LSTM. But why I'm covering LSTM in a simple way at least is LSTMs are the foundation for what we are using the transformer in the current generation. So to understand this transformers and the attention mechanism, this LSTM plays a very important role. So to uh, you know to uh, have that link in understanding what is a transformer and attention mechanism. So that is the reason I'm just covering the LSTM part as well. So if a few people, if you want even more detail, completely the architecture, what are the functions, how it actually performs, the complete even, anyway, I'm just touching the practical part on bidirectional LSTM also. I'm not leaving completely just for a theory. So I'm just, as of today, we will also cover this bidirectional LSTM practical part also. So we'll see that, but still, if you want more from LSTMs, I can cover that. You can just ping me in the chat if you actually need it. Okay. So I would feel that, it has become a bit of outdated compared to the, if you want to say that I want to know the current technology, what is happening. So the LSTMs are a bit outdated compared to the, even attention mechanism also has become a bit of outdated. But what is happening is in a few areas, particularly in transformers, attention mechanism is actually playing a very important. So that is why attention mechanism is still inside the, I would say, important concepts or something very important, which is linking up to the current generative AI technology. Okay, so that is the whole picture and scenario. Now, let us go to the next part, which is attention mechanism. Okay, so attention mechanism, just now I was speaking about attention mechanism, that only. So what is this attention mechanism? What is this attention mechanism, what I was speaking about? So this is a sequence to sequence model. So this can be understood also very easily, because we know that from RNN, right, the upgradation of LSTM has actually happened. Right. So basically, LSTMs are upgradation of RNNs, and and these RNNs were basically used for textual data, right, or a sequence data. So that is why this attention mechanism is actually an upgrade over the LSTMs. So obviously, you can expect that even these attention mechanisms will be a sequence to sequence model. Okay, but there is a very important uh, you know concept. Okay, so this might be a bit of difficult, okay, for you to understand, but I will try to explain not just theoretical part, but also in the practical part also. This becomes bit of completely over the head kind of concept. Actually, this is because this is a concept where it uses the concept of encoder and decoder. Okay, so I think you guys will be aware of what is an encoder and a decoder. So encoding is nothing but compressing. Decoding is again, uncompressing it back. Correct now? In a simple language, if you say encoding and decoding is nothing but compressing it and compressing it back to uncompressing it back to the norm. So that is what encoding and decoding model is. So exactly on that particular part or on that particular concept only, this attention mechanism actually works. So this is more focused on the concept of encoding and decoding models. It's a classical model of encoding and decoding. So why we are using attention? Okay, so the next question comes. So the main advantage of using LSTMs is it can have long sequence of text or long sequence of sentences in the memory. It can hold lot of lot of sentences or a sequence of words in the memory without losing the context, right? And it can compress and it can decompress it back or decode it back without losing the context. That is the main important feature when it comes to attention mechanism, or why attention mechanism has become a success. Because since attention mechanism was success, this was again upgraded as a technology called as transformers. Now, so attention solves this by creating dynamic context vectors. And what are these vectors? We have already understood in word to vector. You remember word to vector we have seen, correct now? So in word to vector concept, I've explained what is inner product space. Then I also told these are completely, related to linear algebra concepts. So you can just, know more about that. So I already told you that probably, those who are interested would have actually try to go there and try to understand. So even this attention mechanism basically focuses on the concept of vectors, right? So it actually creates a dynamic context vectors for each output set step based on a weighing combination of encoder hidden states. So how does this attention works? This is in a very simple language. I have mentioned how this actually works. So now compare the decoder's current state with all encoders' hidden states. So it calculates the attention. Attention is nothing but in a simple way to understand what is attention is giving focus to what is important, right? So what is important in that certain area, how much of importance has to be given in that particular situation is what basically attention is about. Okay, in a very simple language to understand that what is attention. So these actually these vectors which we are computing as weights. So it actually forms a vector using the scalars, right? So this will calculate a vector, it will create a combination of vectors to create a linear equation. Okay, it creates a linear equation. Okay, so then it tries to actually encode, and then it actually tries to decode it back using that context vector. So this is the I think in a very simple way I told. Okay, so this mechanism doesn't happen in this much simple way. Okay, just to understand as an just a outline, I just told you in that simple way. Okay. Right. So now coming to how this attention works. So attention is actually, this is the function which uses the attention. Okay. So first what I'll do is I'll just go to the, first we will see this. Okay. I just wanted to show you this first, and then we can go try to understand what is this attention in a more detailed way. Okay. Now, first of all, what is attention? Okay. So attention is basically applying exact weights, right? Or I can say applying the weights based on the importance. Or I can say, in each situation. See, forget about this concept. Generally, right? If there are certain situations, right? For each situation, you give importance based upon the scenarios, correct? Right? The same way, exactly, this attention mechanism also works in a similar way. So each function, how much of importance it has on that effect, or I can say effect on the next layer. For example, in a deep learning, a model, we have seen that there are multiple layers, right? There are multiple deep learning layers. So there are multiple hidden layers which are there. So each layer is connected by uh, you know, uh, I would say, each layer is basically connected by this functions. Correct now? Now this activation functions. Now, what this attention mechanism actually does is it will try to rearrange. It will try to give importance. It will try to make it in such a way that the importance is actually given at a perfect way, so that it actually encodes in a proper way and decodes it back in a very important way. Okay, so in that way, we it something goes encoder. If you see from the backward, right, from the diagram from the bottom, so it tries to encode, right, and there is an alignment score. There is a decoder's hidden state. From there, it gives the attention for each layer, or each a layer which is having that particular importance. So from that, it will try to understand the context, that why this certain one has been given more attention or more importance. On that, it will act upon. Okay, so acting upon based on that importance and taking a decision and understanding the context based upon that, that is the speciality of using this attention mechanisms. So this will make the model in such a way that what are the key important aspects required at that certain situation. It gives more importance on that particular aspect. So this is how the attention layer actually works. And so this is again the attention layers encoding to the encoding and decoding part. Okay, so I just will go back, and this is the formula for how it actually calculates the attention mechanism. Okay, I told it's completely statistical and mathematical formula, because the activation function itself is basically using the statistical functions. In that particular way only, it will build the hidden layers. So from there, the model building actually occurs. So this attention layer basically tries to calculate by using this function that how much of attention is basically required. Okay, so CI is nothing but finally the attention. So in that you can see alpha ij and hj. This alpha ij formula you can use exponential of eij and divided by summation k is equal to 1 to tx exponential eik. And this exponential eij will come from the formula. This is basically rho, okay, alpha t, alpha to the power t, then tan h, w, alpha si minus 1 plus u alpha hj. So this is the entire structure of how this attention actually happens. So this attention mechanism, we need not bother, or I would say, in a simple terms, we need not by heart this formula, or we did not understand what is happening. But if you really want to understand what is happening inside each attention layer and how this attention is being calculated, so this is the simple formula to understand. Now, let us go to the next part. Okay, so there are especially there are two kinds of attentions. Okay, attention mechanism. There are two kinds. So one is Bahdanau. Okay, so this is found by Dimitri Bahdanau. Okay, so this Bahdanau it has found one of the attentions. Okay. So I told you, there are two kinds of attention mechanisms. Both are used. I would say upon the situation, we can use whatever attention we require. Now, this is basically an additive attention mechanism. So this actually allows the decoder to attend to different parts of the input sequence to each output sequence by learning alignment score dynamically. So you have seen here now in the figure, you can see the alignment scores. See. So these alignment scores are calculated at each stage of that particular layer. How much, these weights will actually change according to the scenario in that particular layer. So each situation or each importance based upon, how much of importance is there, each importance or each, the attention or weights, I would say in a simple language, the alignment scores will change at each situation. Okay. So on this particular factor, this how these alignment scores can actually change dynamically is what the concept of Bahdanau's attention mechanism is based upon. Okay. So we will see this bidirectional LSTM in practical, and then we will also see what is this attention mechanism, what is the sequence to sequence attention mechanism also. We will see that as a practical. And then also this Bahdanau's attention also we will see. Okay. So this Bahdanau's attention also uses that encoder decoder concept, encoder decoder concept of what the sequence to sequence model in attention mechanism actually brings to the table. So this is actually based upon the from the source, you have that embedding layer. So embedding, you are not new. Embedding, we have already discussed word to vector embedding layer. Okay, word embeddings. So I'm not going there again. So I feel you have seen my previous session, I've attended the previous sessions. So you will be aware of what is a word embedding is. So we have already discussed word to vector word embedding. How actually it happens in practical also, I have shown you. So first, the embedding part will happen. Then you can see the recurrent part. Then it will go to the state part. Then the recurrent will happen. Then it will, from there, it will decode it back again. So this is the main mechanism of Bahdanau. So going to the formulation part. Okay. So going to the formulation part again. This is again completely optional. If you want to understand the formulation part. Okay. So this basically is depending upon the alignment score. Okay. This alignment score, I already told you, it uses the tan h function, right? And it actually based upon the states s-1 to the state s, this will actually encode and decode based upon that. And this attention mechanism, it happens through the I would say through this activation function, because softmax is nothing but an activation function. So it uses the softmax function and it builds upon the attention. So it calculates the context. So already we have seen this formulation before, correct now? Yeah. Now let us go to the next one, which is Luong, I can say, right? The pronunciation is like that. It's Luong. So next is Luong attention. Okay. So these four we will try to see as a practical part today. Bidirectional LSTM, attention, sequence to sequence attention, and then Bahdanau's attention and Luong's attention. Okay. So right. So let us understand this first, and then we'll get this theory part done, and then we'll go to the practical part. So what does this Luong or Luong attention actually mean? Okay. This is in that fellow's full name is basically Min Thang Leong. Okay. So this attention is also found in the year 2015. Even Bahadana's attention is also found in the year 2015. Okay. So they both actually happened simultaneously. So this is a variant of attention for sequence to sequence model. So that we already know, right? So for attention mechanism, particularly for sequence to sequence models, we are using this Bahdanau's and Luong attention. So this is particularly effective for machine translation, which all the AI models currently in the generative AI basically use. So this is basically this is bit different from the Bahdanau's attention. Now, what is different from Bahdanau? We'll try to understand. So unlike the Bahdanau, which uses decoder hidden state before decoding the current word, right? Luong computes attention using the current decoder hidden state and all encoder hidden states. So this is the difference between what happens in Bahdanau and Luong attention, and this will make you more, it will make more sense when we go into the practical part, because I'll explain step by step and how this actually works. So, you'll be in a better position to understand how this encoder and decoder concept works in both Bahdanau and Luong attention. So this is the process of how each step happens. So first it uses the inputs encoder, and it tries to calculate the or use the outputs of a hidden state. So then it decodes the hidden states, right? And it compares all with the encoders. So based on that, attentions are calculated or weights are calculated, and then the vector is basically uh, formed and used. Okay. So the weighted sum is calculated from the encoders, and then the decoding text is actually again used back. So this is the basic, I would say, this is the basic principle of how this Bahdanau is basically used. Sorry, this Luong is basically used. Okay. So yeah, now let me go to the first practical of the four. Okay. So I told we will see four concepts. So yeah, this is basically, let us start with the first one. So let me share my screen. Sorry, collab. Okay. Okay. So now I've just shared the first one, which I wanted to discuss today, the practical one. The first one is the bidirectional LSTM. Okay. So this bidirectional LSTM, right? We'll start with this. Okay. Now here, I just would like to add a few things. Okay. Now, first of all, we'll start with importing of the necessary libraries. Okay. And we have already known a few things. One is, importing of TensorFlow. Okay. So the first one is importing of the TensorFlow. And so those who have not known TensorFlow, for them, I just wanted to just, put one line. Okay. So you can see now. Okay. Just searching for that line. So it's basically an open source library, right? Which is basically used for building a deep learning model. So that is what basically a TensorFlow basically is. Okay. So let us go step by step in order to understand. Okay. First, that is what the TensorFlow. So to import the TensorFlow into the into our Python notebook, we can call it by import TensorFlow as TF. TF is the alias name for TensorFlow. Next, what we are doing is we are importing the sequential. Okay. So what is the sequential is? Sequential is nothing but a sequence of layers. Okay. 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 So now you can see. So as the name suggests, the sequence is nothing but creating a sequence of layers, or I would say layers in a sequential way. Okay. As like a linear stack. That's what the technical word we use. Okay. So it's basically like a linear stack or something which can be arranged in a order. So that is what the sequential is basically used for. Okay. Now let us go to the next one, which is for embedding. Okay. So I already told you what is embedding anyway. Now I'm just giving you as a sentence. Okay. So embedding is basically used to convert the indices into the vectors. Okay. Let's remove this. Now, the next layer, the next one is the bidirectional. So anyway, you already know bidirectional is nothing but applying the model or layer from both the directions. Okay. So that means wrapping the RNN layers like the LSTMs to process the inputs from both the orders, which is which is from the forward as well as the backward order. So in both the directions, the layers will be applied. So that is one thing. And next is the LSTM. Okay. So LSTM, already we know what is an LSTM model. It's a long short-term memory layer, right? So this is basically used for sequential data. Okay. So to, for processing or building a model for sequential data, we are going to use these LSTMs. Okay. Now, the next one is we have dense. Okay, so dense is basically nothing but it is basically used for something which is connected. Okay, so a layer which is connected, we can use the dense. Okay, so that is why we are going to bring these four into the. Okay, we are going to bring into the Python. Okay, I hope till here it's clear. Now, the next part is we are basically bringing in the data set. Okay, so this data set. Okay, so this basically a data set. This is basically a data set which is used for training the model. Okay, so we are building we are basically building a sentiment analysis, I would say. Okay, and for this we are actually bringing in the data set. First of all, the data set is the IMDb data set. So, some of you might be knowing this IMDb. So IMDb is a international movie database. Okay. So this has the list of all the movies which are there. And along with that, it has the review part as well. So what are the people's comments and what are the reviews the reviewers has given. So this website or an application which has movie reviews and it has the list of movies along with it. So this is a default database which it is there inside the TensorFlow. Okay, so you can use this IMDb dataset for analyzing this sequence of I would say reviews for the movies. Okay. Now, next is the next line. What we have is the padded sequence. So now let us add what is the padded sequence. So this padded sequence, let me add first. Okay, on this is also a big line. We'll make it into two. Okay. So now let us see what is this padded sequence. Okay. So this padded sequence is basically nothing but it inputs the sequence of words. The name itself tells you it's a sequence, right? So what it is basically sequencing is it is sequencing the words, right, based upon the length, the sizes. Okay. So this particularly the function pad is basically nothing but to truncate. Okay. So it will actually try to truncate or pad it to the uniform length so that it can be processed in batches. Okay. Or it can be processed in group. Batches are nothing but equal size of random samples is what batches is. So to process this, it tries to put it into shorter lengths or a uniform length. I know I should not say shorter length. I should actually say uniform length in order to process the data uniformly. So this is the main advantage of using the padded sequence. So these are the libraries which were actually importing into the we are importing into the I would say we are importing into the Python, right, for applying this bidirectional LSTM. Now, I think till here it's clear for you. If you have any doubts, you can ask me if you have anything. Till here, it should be fine. Okay, because till now I have not asked anything. So probably anything else also, if you have, you can ask me doubt. I'm just giving you a couple of minutes. If you have anything, please you can ping it. Or else I'll just continue from the after importing the libraries, what we have to do in order to apply the bidirectional LSTM. I'll continue from there. Okay. So I think nobody has any questions. Probably during the break time, if you have, you can post it. Okay, fine. So let us continue then. Now, we have to load and pre-process the data. So that is the next step, what we have to actually do, right? Now, here we are saying that, okay, so I'll just put one line for loading the data set. So what this actually does is, okay, yeah. Here you can see that this is, this data set has commonly, 10,000 most commonly used words or vocabulary is there in this particular data set. Okay, so that is why we are using this IMDb data set. Now, and we are using, we are actually using this 10,000, we are keeping this as a limit. Okay, we are keeping the limit of 10,000 to limit the number of words. Okay. Now, let us go to the next part, which is loading the data set using the, I'll just add a comment here. Okay. For this X train and Y train. Okay. So I think you have to add a few things. Okay. So basically this X train, this is a list of movies, okay, for training purposes. Okay. The next part is the Y train. Okay. So this Y train is we are using to train the data, okay, to understand whether it is a positive review or a positive label or a negative label. Okay, to give you the numbers or to give the labeling. Either it is if it is a negative, we are going to give 0. If it is a positive, we are going to give 1. Okay, so that is one thing. And so X test. So I think anyway you can understand what is X test. So X test is nothing but to test the reviews, and Y test is for testing the labels. Okay. Yeah. So this is the main agenda in writing this particular function. Okay. So what we are exactly doing is we are training the data set for identifying the indices in the words, right? And we are trying to identify the positive and we are trying to identify the positive labels or the negative labels. For positive, we are giving 1, and for negative, we are giving 0. So this is the main aspect in what we are trying to do. Okay. Now let us go to the next part, which is the padded sequence. Okay. So for this padded sequence, here we have mentioned a maximum length of 200. Okay. So what is this 200 actually is? Wait, I'll just put a comment here. So what is this basically 200 is? This 200 is the fixed size for the neural network. Okay, for the training purposes. So it's basically better, or it is actually better to give the fixed length, right, in order not to have any conflict. Okay, so the next part is this extreme. Okay, so for this extreme, what it is does is in a simple in a simple solution, in a simple way. So this particular extreme here in this scenario, when we are using this padded sequence, this actually ensures all the input samples are of equal length so that they can be fed into the neural network in a batch. So I told why we are using this padded sequence. So it will create that uniformity, okay, in order to train the sample, right, in a batch. That is what exactly this padded sequence actually does. Okay. So now let us go to the next part, which is X test. Okay. So for X test, it's the same thing, that the testing samples should be in a same size, right? Or it will be in the same shape to test the evaluation purpose or the evaluation purpose. Okay, so that is the main aim of using the X test, or you can say padded sequence for X test. Okay. Now I think we have added so many comments. Okay, now let us go and build one bidirectional LSTM. Now here, when we say the word sequential, I have already, discussed. Let's add one comment here. So when I say we are doing a sequential model, this starts building a sequential model which allows you to stack layers one over the other. So we have already seen what is the sequence or stacked layer, what we are actually doing. Now let us try and understand that the next function is the input dimensions. Here you can see input dimensions, which is the number of words. So for input dimensions, we have set the vocabulary size to 10,000. Correct now? So since we have set the vocabulary size to 10,000, it will start ordering the words with indexes, right? It starts ordering the words with indexes, and the indexing will actually start with 0, right? So because the array indexing starts with 0 and it ends with 9999, 4 nines, right? So it starts with 0, it ends with 9999. Okay. So, if it starts with 0 and ends with 10,000, then it becomes 10,001 words, right? But our vocabulary, we have set it for 10,000. Okay. So that is what this input dimension is basically about. Now, the next one is output dimension. So what is the output dimension we need? So the output dimension, what we are taking is a 64, dimensional vector. That is what we are given. See, that is why we are given output underscore dimension is equal to 64. So this tells you that the output will be a 64 dimensional vector. Okay. Now, going to the next part, which is input. Okay. And here you can see. So you can see that the input length, what we have given is the maximum length, right? So this is basically the length which we have actually fixed it to 200. Okay. Now, this is what we have done. Now, the next thing is we have given, I think you are aware of this LSTM. So I'm not again adding this as a comment because what is this bidirectional from both the, if you want, we can add it anyway. Okay, maybe here, anyway, it's fine. I will add it here. Okay, again, few people again will have doubt. So just adding here. So here we are applying this LSTM model with the 64 dimensional vector. That is one thing what we are doing. And apart from that, we are also doing this bidirectional. Okay. This bidirectional is nothing but applying the input sequence from both the directions. That is what this bidirectional basically is for. Okay. So this will help to understand the context in a better way. Okay. So that is the that is the comment which I wanted to add. So apart from that, what we are doing still, we are giving the dense. Okay. So what does this dense layer actually do? So this dense layer will create the depth in the layer. Okay. And okay. What I'll do is, wait, for dense also I will add first. That will be a better thing for you to understand. Okay. It's good, no? If you add comments, no problem. Extra comments are not a problem. Okay. So this, what it does is it will add a dense layer. Okay. Let me reconnect. Okay. Now, if you see here, we are adding a dense layer. Okay. So this Sorry. So this dense layers are basically fully connected layers. They are basically fully connected output layers. Okay. So, and here it is using a dense of 1, which indicates that it is one layer and it is using the sigmoid activation function. Now, here if you see, we are applying the sigmoid activation function, and sigmoid function is a, it's a, I would say, it's a classifier model. It's not a regression model. It's a classifier model. And what it will value is the values will be between 0 and 1, which are used for binary classification. Okay. So this is what exactly is going to happen here. Now, let us go to the next part where we are trying to compile the model. Okay. So here we are applying the loss function, which is cross entropy. Now let us understand what is this cross entropy. So this cross entropy is nothing but a loss function. So loss function in a simple term for you to understand is, uh, the difference, or you can say the difference between the actual versus the predicted value. So the difference between the actual versus the predict value is basically called as the loss function. Okay. So whatever the loss function should be very minimum, then only the model has been built in a very good way. So because what you are predicting and what is actual should be very close by. Now, so next one is the optimizer, which is Adam. Okay. So Adam is a very popular uh, optimizer inside deep learning. So more than popular, I would say it is more effective. Okay. So it is more effective. So that is why we are using the system. Okay. So, telling that it is more popular, I would say, we can say that this is more an effective way of optimizing. So that is why we are using ADP as an optimizer. So now the next part is the metrics part. Okay. So this metrics is basically nothing but which is basically used for checking the accuracy score. Or we can say that this actually tries to identify the difference between the training and the valuation score. So that is the job particularly of the metrics. Okay. And the next thing is the model summary. Okay, the summary gives the it prints the output. You can say it prints the output. It gives you the layers, it gives you the output shares, it gives you the number of parameters. So everything will be given in the form of output. Okay, so that is nothing. So next is before going for a break, just let me finish this. And the next part is fitting the model. And here you can see that we are fitting the model. Okay. And this model dot fit, what it does. Okay. So what this basically does is it takes the X train or the input values, right, which is in the form of X train and Y train for the independent variable and the dependent variable. And it tries to propagates or it tries to fit the entire data into that particular model. So for X train, basically, right? For X train, I would say we can say that it basically represents 200 tokens. So what we have actually inputted. So this becomes a fixed length of inputting the 200 tokens. So now for the Y train, right, it tries to label whether it is a 0 sentiment or a, okay, it tries to take the 0 sentiment, or I would say uh, 0 for negative sentiment, and for the, so this number of epochs, epochs I already told you, no? Epochs are nothing, epochs, EPOCHs are one full cycle of training is what basically an epoch is. I'm just giving a simple way. Okay. So epoch is nothing but giving the training, doing one full cycle of training is what basically an epoch is. Okay. So now next is batch size. Okay. So batch size very easy to understand again. So batch size is nothing but building the number of one sample or one batch has to have how many number of samples. For example, if we give 32, it will have 32 samples in each batch. If we give 64, it has 64 samples in each batch. So it will divide the samples into batches. Okay. So that is what this basically, and validation split is nothing but just giving how much of percentage of training data and all. So if you say validation 0.2, the testing data will be 20% and training data will be 80%. Okay. So that is the use of giving the validation and or we can say either we can give the training data or we can give the validation split. Anything you can give. So if you give a validation split of 0.2, so that the testing data will be 20% and training data will be 80%. So that is how it is going to run. Okay. So after that, the next part is the model evaluation, right? So the model evaluation, so the first one, wait, I'll just post one line, which is very important. That is very important. Based on that, you'll understand. So what this will actually post is, for this X test and Y test, it will give two things. One is loss function and one is the accuracy score. Okay. So loss function, I told you already, this is between the actual and the predicted value is what the loss functions. So accuracy is how much of accuracy we have got by building the model. How much it is able to predict the real value. That is what basically an accuracy score is about. So it is about that how much it is able to actually try to generate, okay, or how much it's able to test it. Okay, so we run it again. Okay, I've added several comments. So let me just run it again. So anyway, let it run. I'll share this anyway. So probably we can just go for a quick break and come back. And you can post your questions in the chat. Okay. Yeah. So yeah, usually we go for a break at 8 o'clock. Today it became a bit late because we are discussing the concept of bidirectional LSTM. Okay, no issues. We'll go for a quick break and come. Okay. And after that, we'll try to understand what is attention mechanism. Okay. Yeah, all of you, you can just post your questions in the chat if you have any. After the break, I'll just come back and answer your questions. Okay. Okay. So I think I think everyone has come after the break. Fine. So let us continue. Right. So let us see the second practical of the day. Okay. So let us go to the attention mechanism concept. Okay. So this is actually a bit big concept. So how much ever is possible, we'll cover the attention mechanism today. The rest we can continue tomorrow. After that, we'll go with the Bahdanau's attention as well as Lango's attention. Okay, so let me share my Python screen. Okay, right. So let us try and understand what is this attention mechanism. So we have actually, tried to understand that what is this attention, theoretically. Okay. So we have not gone into practical part. So that is what we are going to do now. Okay. So the most important part of our attention implementation is it is very important for you to understand that this attention concept is basically a sequence to sequence model. Okay. So this is basically a sequence to sequence model. That is what this attention mechanism is about. So, and we have also discussed that this attention mechanism is a concept of encoder decoder technology. So that is also we have understood by understanding the concept. Okay, so how this is implemented now, let us see. Okay, now I would actually want to add a few comments. Okay, I just wanted to add in front of you that is why I've not added any comments on this. Okay, I've kept it aside so that during the session I can add a few comments. Okay, and this attention mechanism uh, is actually implemented using one of the very important technologies, which is called as PyTorch. Okay, so probably a few you would have heard. Okay, so probably would have heard. I hope you would have heard. Okay. Now, the first part is what I have actually written is I've given the word torch. Okay. So what is this torch is? Torch is nothing but it's a core library. Okay. Inside PyTorch. So we are going to import this torch into the, we'll say, issue that it's a module. So see here. So the torch package contains data structures for multidimensional tensors and defines mathematical operations over these vectors, over these tensors. Additionally, it provides many utilities for efficient serialization of tensors and arbitrary types and other useful utilities. It has CUDA counterpart that enables you to run your tensors computations on an NVIDIA GPU with compute capability greater than or equal to 3.0. Okay, so what is this NVIDIA CUDA course and all? I have a separate session on that only. And one day we'll speak on what is this CUDA course inside NVIDIA and all those things. What is this powering and all? Everything we will talk it again. That is another bigger picture to talk about. So let us try and understand this torch technology we are actually using for implementation of this attention mechanism. So next thing is the torch.nn, right? So what is this torch.nn is? This is basically NN means the neural network. Okay. In a simple way, you can remember that this NN indicates that it is a neural network. Okay. So how to access the neural networks inside PyTorch? We are going to give torch.nm. That is one function which we are going to give. Okay. For that, we are going to give the alias name, which is nm. Okay. So till here, sorry. Till here we have seen. Okay. Now let us go into a bit deeper. Okay. So next thing is we are actually defining the okay. Now let us break down into small steps and try to understand. That is why I'm adding comments also, because even for you, for future reference also, it will be useful. Okay. So here we are defining a particular class, which is encoder. So here class encoder is nothing but a function. It's a user defined function, we can say. Okay. So here it actually inherits the class encoder, right, which is a function, right? It inherits from the NN module, which is the which is the neural networks module. So this will inherit all the features. I think few of you already know the concept of OOPS, right? Object-oriented programming structure. So in that we will see the concept, C++, Java, Python, everything has this. So you will see a concept called as inheritance. So inheriting from a parent class. The same thing we are trying to do. Here the parent class is the NN, which is the torch.nn. So from the torch module, we are inheriting the features which we want for the encoder function, which is the user-defined function. So this is the common thing what we try to do inside the PyTorch. Okay, so that one you can remember. Okay, so now let us go to the next part, which is here init. Okay, so you can see here underscore init underscore. So this will actually create a constructor. Okay, so let me just put it here only. Okay, all the comments I'll put it here only. Okay, this is because this is one block of code. So if I again touch it, here it goes here and there. So what I'll do is I'll just put the you know all comments here itself. Okay, so here we have a so constructor is nothing but something which actually defines. Okay, it is like a class, or you can say as a user defined function. Okay, now here we have in that particular constructor we have something called as the first one called as input dimensions. You can see here, see. Okay, so what is this input dimension is? It actually tries to define the size of the vocabulary. Okay, this input dimension will define the size of the vocabulary. So that is the first important thing of input dimensions. So next thing is the embedding, EMB underscore dim, right? So this is basically used to, define the size of the vocabulary, or I can say not vocabulary, the embeddings. So we have already understood what is an embedding and all. So I'm not going to go there. Okay, so this will actually give you the size of the word embeddings. So the next thing is hid underscore dim. Okay, this actually tries to find the hidden layers for the model GRE. Okay, so what is GRE we have already seen. So the next thing is n layers. Okay, so n layer indicates the number of layers in the group. Okay, so GRU is nothing but gated recurrent unit. Okay, so those who are aware of it already, fine. Okay, so the next thing is the dropout. Okay, so the dropout function helps the layers to drop before the model gets overfitted. Okay, so it actually tries to prevent from overfitting. Okay, so that is the advantage of using the dropout function. Okay, and then we have one more, which is the function which is super underscore. So actually it's a super dot, double underscore init double underscore. So this function initializes the base class. Okay, so this is the main mechanism, okay, in actually launching the function. Okay, now let us go to the next part. Okay, let us go to the next part, which is the embedding layer. Okay, here let us talk about what is an embedding layer. Okay, here we have, correct, no? I think it will be better if I put it here. That will help you to Okay, this self dot embedding, which is input embedding and embedding dimension. So this actually converts each token, word token, into a dense vector. That is what this embedding layer will do. So this will take the shape of input tensor as a shape. Wait, I'll just put it here. Okay, so this is comments for this embedding layer. Okay. Yeah, this is enough. Okay, so this will be enough. Or I would feel this only I will put in one line. This should help. Yeah. Okay. So this is for the embedding layer. Okay. So this is for the embedding layer. I'll just enter it like this. Okay. So here what is happening is for the embedding layer, and I'm using this input dimensions and embedding dimensions. So what it does is basically it converts each word as a token and it creates into a dense vector. Okay. So that is the use of using this self embedding concept. So after that, let us go to the next one, which is self.rnn. Okay, self.rnn. So RNN here is the recurrent neural network. And for that, we are applying the function, which is, I would say, the GRU function, which is gated recurrent unit. Okay, so that is what we are, actually written. So what we'll do is we'll put just one comment for this. Okay, so what this does is this input layer here, which is the embedding dimension, this will actually give you the input size. Okay, after that, there is one more called as a hidden layer, hidden dimension, which will give the hidden size. Okay, so after that, there is one more, which is the layers, which will give you the number of layers. Okay, after that, there is one more function, which is the dropout. So if n layers are greater than 1, okay, you can use it will actually try to drop out. Okay, so for that, we can use this dropout function. Okay, in that way, this will be useful. Okay, so self dropout we have actually applied. So what this actually does is this self dropout. So during the training, randomly, if something is not right, it will drop out in order to prevent the overfitting. Okay. Right. So see here. So randomly zeros some of the elements of the input tensor during the trainable with the probability dropout. So this is the main advantage of using the dropout function. Okay, in a simple term for you to understand. So in that way, you can figure it out that what is a dropout. Okay, now coming to the next part, this is the first step. Okay, there are five steps in what we are trying to implement this attention mechanism, which is sequence to sequence mechanism. So we are in the first part. So in the first part, we are coming to the next function, which is the function, the forward method. Here we are applying define forward indicates. We are defining a particular function. The function name is forward. Okay. So it is like a feed forward network on. That's it on it. Okay. Now let us go to the next part. Okay, which is embedding. So this self embedding actually helps you to I'll just put one line of this will help you to understand better. I'll just put one more line here. Okay. Yeah. So here I've taken a function which is, see carefully, self-embedding SRC. Okay. Here I have implemented this SRC here. See. Okay. Okay. Now here I've given the same function which is self.embedding. So what this will actually do is it will turn the input indices into dense vectors. Okay. Because we are using that particular where it is, we are using this GRU, gated recurrent unit. Okay, you can do some research on GRU later. Okay, fine. Now this is what this thing will do. Now going to the next one. So anyway, self drop you already know. Self underscore drop probably if you want. Okay, fine. I'll just mention that as a comment as well. Probably that should help you as well. Okay. So what this will do is self drop will drop. Yeah, apply. It will appear on its apply on its own whenever it want to regularize the model. Okay, that is the main advantage of using the self dot dropout function. So whenever it want to regularize and whenever it wants to, or whenever it identifies that the model is actually overfitting, this will try to regularize, or this will try to adjust the hyperparameters accordingly. Okay. So the next part is the GRU's computation. Here you can see output layer as well as the input layer. So here you can see different outputs, inputs, so many things they have given, right? Basically this output layer, sorry, the hidden layers are nothing but the layers which are hidden. So obviously you know that already. So all the hidden layers, whatever are there, will be out. You will get the output based upon the training what you have given. So now this is the first step, or I would say this is the main step, because this is basically about creating a constructor. It is about creating, first of all, importing the necessary libraries, and then building the, or we can say building the constructor and actually creating a user-defined function, and in that inheriting the features of the neural network models which are there in the PyTorch. Okay, Python torch. So that is very important. That is what we are trying to do here. So after that thing, what we have done, we have tried to embed the layers, and we have applied these neural networks into the GRUs, which is gated recurrent units. And then we and to regularize the, not to allow the model to overfit, we have tried to apply the dropout function as well. So dropout is a very important key feature in deep learning. So that is the same thing we have applied here, and we are trying to apply the embeddings also. Now this is the first step in applying of the attention mechanism. Now let us go to the next step in applying the attention mechanism. So here, to implement this subtask of applying this attention mechanism to a sequence to sequence model, the first thing what we can actually do is we try to create a encoder and we try to create a decoder. Okay. Now, the very important thing is creating an encoder. Okay. So how to start creating an encoder? Okay. So, that is very important when we try to create. Okay. Now, the first thing is here we have given torch.nn and functional, right? So for this, let me add a comment. Okay. So let me add a comment. Okay. What this will actually do is, okay, here, let us say, for example, softmax is imported. Okay. So here, usually the PyTorch function, softmax is one of the important activation functions which is used. Okay. So this, this function here, we can use it for both forward pass as well as the backward pass. We have seen bidirectional. Okay. So in the same way, we can use it for both. Now here we are using for F. What is this F? F is nothing for the forward pass. Okay. First we are using for the forward pass. Okay. Now after that, we are creating an attention. So this attention is basically, you can see here, we are creating an attention. So here the class is attention, and we are importing this module, nn.module here, what we have imported here, see in the first step. So whatever the features are there inside the neural networks, you can see here, see. You can see here, it is showing. Whatever neural networks you have, or whatever functions which you have inside the torch, PyTorch, uh, you know, library, all those can be inherited into the encoder class. The same thing we are trying to do here. We are creating an attention because the mechanism is about attention mechanism. Okay. So it is trying to create an attention. Okay. And how this is actually trying to create. So let us see. Okay. First, after that, we are actually defining, uh, you know, which just let me put a comment here. So here we are actually giving the first of all we are giving the encoder which is with the hidden dimension. So what is this hidden dimension I have mentioned here? Okay, there are a few things I just want to mention here. Okay, and the next one is this hidden dim. Okay, let me just put it here. Okay, and after that we have this attention thing also. Let me put it. Okay, and then we can discuss. Okay. Now let us talk. The first thing is we can put it in 5. That will be better. It's okay. Even though this goes a bit high. Yeah, the code goes to no problem. The first thing here we can see that this is encoder hidden dimension. So this function already you would have understood. So this basically counts the hidden dimension of the encoder. So first we have to encode, then we have to go for the decode mechanism. So here you can see that this decode one will be a hidden dimension for the decoder. See here. Okay, this DEC indicates that it's a decoder. This ENC indicates that it is an encoder. Okay. Now this ATTN underscore dimension indicates that the size of the attention what it actually wants. Then the first thing is self-attention. So we will not put our hand, or our, thinking into that. So what we will do is we actually leave the, encoder and the decoder to, build a layer on its own because this PyTorch is capable of doing that. So what it will do is it will try to build a linear layer compressing the both, which is encoder and decoder. So basically what this will do is it will concatenate, or it will put both together. Okay. So it will actually try to build, I would say in a very simple language, it will try to put them together. Okay. And it will try to build. So that is what the main importance of the self attention mechanism, what we are trying to use. So the next thing is the self.v. So this actually tries to use the attention's dimension and it will try to build. So here you can see that this self.v is it's nothing but it is going to build an attention score. We have seen in the presentation I showed that this actually calculates the attention score. So this is the exact function what what calculates the attention score. Okay. So now going from that to the next step, we are building a forward pass. Okay. Here you can see we are defining a function called as a forward pass. Okay. For that forward pass, we are giving the we are defining the function which is self, hidden, and the encoder outputs. And the next thing is the batch size we are giving. So batch size, tries to identify the number of size what it actually wants. Okay. And the next thing is the hidden layers. So how many of hidden layers actually we want to give, right? Because we are also mentioning the dropout when it has to actually drop out. Okay. So after that, there is one important function I would actually like to give you, which is that just a minute. This energy is equal to tan h function. I have a comment for that. Just a minute. Just add that. So forward pass, then batch size, then we have the hidden, yeah, here. For tan H, I have a comment. Just add one. Yeah, this is very important. You'll understand why I've added this. Then this is the tricky part here. Yeah. So this is the tricky part here. So what happens here is this tan H function, you can see here, it concatenates each hidden state with the decoder state. Okay. And this applies that tan H function. Tan H here you can see H. After that tan you can see H. H is nothing but a hyperbolic function. Probably you would have heard in trigonometry, right? Many of you would have studied in trigonometry. So H is nothing but a hyperbolic function. And this tan H is a hyperbolic function of tan. Okay. And this is a, one of the, not, I would say not most common, one of the mostly used only, but not that used like softmax and all. But tan H function is also used as an activation function. Okay. So here in our self attention, while building this hidden layer, we are using this tan H function. Okay. So in the PyTorch or torch, what we have given, so we are using the tan H function here. Okay. So that is what you can understand from this. So now going down with that, we are applying the layers with the batch size. I think 1 we have given. Where is this? Yeah, batch size 1 we have given, and then we have given to return with the softmax. Okay. So for this, I just want to add one comment. Yeah. So what this actually does is it will return or it applies softmax. Okay. So softmax is basically used for nonlinear. Okay. So probably if you go to an activation function, softmax will be seeing the formula for that, which is 1 by 1 plus e power minus x. So that is the basically that x indicates the linear equation form which we see for a linear regression. Okay. So based on that, only the softmax activation function is basically developed and which is actually used. And this is one of the most common normalized because this will actually normalize the weights and this will actually apply the weights to the to calculate the attention. Okay, so that is one thing. Now here the next step is we are applying the decoder for what we have actually encoded. The first step is we have encoded something, right? For that we'll try to decode. Okay, so for that we are applying the forward pass. Okay, and we try to calculate the decoding part as well. Okay, the same thing what we have done for the encoder, we are going to apply that in the same way, and we are trying to apply the dropout here in that same way. So for creating the decoder also, we are going to inherit the we are trying to inherit the features of the PyTorch into the from the module NN. Okay, so whatever features of which are there in the neural network inside PyTorch will be embedded into the decoder. Okay, so this is the main important aspect. And the same thing, I'm applying the neural network inside the GR. Okay, or I would say group. Okay, created recurrent unit. So the same thing I'm applying. Okay, I've added the comments anyway. Okay, at each point. Probably if you have any doubts, you can ask me also. So this is the step where we try to decode it back. What exactly what we have encoded here. Okay, so decoding step will be little bit bigger compared to that of the encoding step. So this encoding, whatever we have done, we try to decode it back by using the attention mechanism. This is just a small example of how actually attention works. So similar kind of coding and similar kind of implementation part you will see in this Bahdanau's attention as well as Luong attention. And you will also see, because transform is also an upgraded version of this attention, you will be seeing a similar kind of similar kind of mechanism inside this attention. Sorry, inside this when we are implementing transform also, similar kind of implementation part you will be seeing. After that, after this encoding and decoding part, then we will have this combination of both encoder and decoder. So we are going to combine both encoder and decoder. See here, you can see. So we are trying to combine both encoder and decoder. And for this, we are going to use the modules, encoder, decoder, and the attention modules, what we have actually defined. And we also will use the constructor, init constructor, what we have actually created. And we are going to use the forward pass for building this. Okay, so that is what the outer picture of what we do for attention mechanism. Probably you can try this. Okay, so word embeddings and all. I'll just explain this again tomorrow. Okay, this particular part I will explain. Okay, this particular part, this first two parts, building an encoder and building a decoder. Leaving this, I will try to explain that combining these two, what we are trying to actually achieve, and from there, what are the subtasks, like how we are training the data, and how we are actually building the model. That we will try to see in tomorrow's session, and then we'll go to that Bahdanau's attention and Luong's attention. Okay, so that is what I'll try to do. So I know this is a bit on the heavier side. I can understand, but this is how generative AI works. Okay, so that is what in reality, and what we think what generative AI is. So that is completely, so that completely has a huge amount of coding and training behind that, what is actually happening. So if you have any questions, you can just ask me. Okay. So even tomorrow's agenda, I told you, we'll continue from that attention mechanism part. And from there, we'll take it over. And then we'll go to the transformers part. So we have a couple of minutes. I actually didn't get a chance much to ask you questions today because, there's a lot to discuss. So what I'm doing is I'm not sharing this attention mechanism with sir. Okay. Only the bidirectional one I'm going to share. Okay. And this attention mechanism, after the end of tomorrow's session, I will share. Okay. So that should be better. Along with that, I think Bahdanau's attention also we will complete. Okay. At least Bahdanau we will complete along with the and Luong also might complete. Okay. Because tomorrow directly we'll go into the practical part. No, there's no theory to talk about. First, we have to apply the attention mechanism, and then Bahdanau, and then we will go with the Luong attention. So I think probably three practical part, the one way almost half, and the other two can be completed, I guess. Okay. Because there's no theory to start. So it will be easier in that way also for us to complete that. So bidirectional I've shared. Okay. So you can use that along with the bidirectional and PPT also and share it. Fine. If you have any questions, you can just ping it on the chat. We have a minute left. Sir, I think we can wind up. Nobody is asking anyway. It's 9 also.
Sure, sir.